All right, this is our last lecture for IB Topic 5. We're going to take a look at how currents experience forces from magnetic fields. If you remember in the previous lecture, we looked at how um, currents or moving charges actually create the magnetic fields that then push or pull on magnets. So a current creates a magnetic field, which means a current is a magnet. And then that can push or pull on other magnets, which are caused by other currents. So really what we're talking about is currents pushing or pulling on each other or exerting torques as magnets. So currents, we know charges can push or pull on each other, but this is a different phenomenon. We're looking at the magnetic interaction rather than the electrical interaction between the charges. Electrical interactions happen when charges are sitting still or moving. The magnetic interactions are only caused by the movement of the charges, and therefore forces are generated. So because of the three-dimensional nature of this, we're going to learn another right-hand rule to figure out which direction charges or currents will be pushed. I know how to draw arrows that point left, right, up, and down. I need a way of drawing arrows that are coming out of a drawing or going into the drawing. So our method for drawing an arrow going into a drawing, something that points away from me, will either be a circle with an X in it or just sometimes simply just the X. And you can think about this if you're firing an actual arrow out of a bow and the feathers, you're seeing the feathers as they move away from you, it has that kind of X appearance. Whereas something that's coming out of the page or out of the drawing looks like a circle with a dot or just a dot. It's the tip of the arrow, if you get my point, headed towards your face. Okay? So that's my notation for the directions. So suppose we have a current. Let's suppose this is a current carrying wire, and maybe it's hooked up to some larger circuit and therefore carries current I to the right. And that current is present in a magnetic field. And so we have the magnetic field. It has some magnitude B. Remember, that's the flux density of the magnetic field, a measurement of how strong in Tesla the magnetic field is. And suppose that those field lines point into the diagram. So they're going into the picture, and then the current is flowing in this direction. In this particular orientation, the current is going to get a force. Okay, so this magnetic field is caused by something else. And then remember, the current itself is a magnet, so it's going to interact with this field just like two bar magnets would interact with each other. And this force is called the Lorentz force. And it's the force a current experiences by being in a magnetic field. A couple of things to recognize is that the current only gets the force if it is perpendicular to the field lines. So since the field lines point into the diagram, anything that's in the plane of the paper, whether it's to the right or upward or to the left or even at some angle on the paper, is going to be perpendicular to something that points into the page. On the other hand, if my wire went in and out of the page, then it would be parallel and it wouldn't get a force at all. Only when charge cuts perpendicularly across a magnetic field. The force is also always perpendicular to the current. And we'll talk about that. There's a right-hand rule to figure out the direction of the force. The magnitude of the force is given by the following expression. The size of the magnetic field times the size of the current multiplied by the length of the wire in the magnetic field times the sine of the angle between them. So Bill sine theta. This one's on the IB data sheet. Force on a current in a magnetic field. As that current interacts with the magnetic field, its own magnetism interacts with it to create this effect. And then I guess I could write L as the length of the wire in the magnetic field. So if the wire extends beyond the magnetic field, those parts don't get a force. It's just the part that's in the magnetic field. And then theta is the angle between the direction in which the charge is flowing and the direction of the magnetic field. So in this case, the charge is flowing to the right. The field points into the diagram. It's 90 degrees. If theta is 0 degrees, the sine of 0 is 0. So parallel or even 180 degrees to each other is going to yield no force at all. How do you know the direction of the force? Which way is this wire going to get pushed? Is it going to get pushed in the direction of the field? No. It's going to get pushed perpendicular to the field, 90 degrees to the other two vectors. And there are two kind of ways you can do this. Actually, there's more than two ways, but here are two ways. And one of them is used in a lot of Chris Hamper's materials and textbook, In Thinking website. He uses something called the Fleming left-hand rule. And you, as the name implies, you use your left hand, and there's a way of like representing the vectors. If you like this, by all means, feel free to use the Fleming left-hand rule. It's not my preference. In fact, I'm going to suggest another right-hand rule, and I didn't actually invent this, so I call it the Filman right-hand rule, but it's just, I don't know, it's another right-hand rule I'm plagiarizing, I guess. What I like about this version of the right-hand rule is it gives the same result, and you use your right hand. And remember, we had a right-hand rule, the grip rule, for what the field lines around a current look like. This rule is similar. You still use the same hand. You don't have to worry about, for sometimes you use your left hand, sometimes you use your right hand. And it's a rule about force. And you use your hand to push on something. You think about your palm as being what pushes. And if you remember in the grip rule, when we gripped a wire, our thumb was in the direction of the current. We're going to keep that consistent here. The thumb is going to be in the direction of the current in the magnetic field. And then my fingers of my right hand are going to be like the field lines. And I've got 4 fingers, parallel fingers. So they're going to be those parallel field lines pointing in a certain direction. So if I look at the one here, okay, what I'm going to do is I'm going to take my right hand and I'm going to point my fingers into the page in the direction of the field lines. And then I have to point my thumb of my right hand. So let me kind of zoom out here so you can see what I'm talking about. I have to point the thumb of my right hand in the direction of the current. Now the current is to the right, so the way I'm holding my hand here is no good. I got to rotate it around like this, okay? So now my thumb, my right thumb, is pointing in the direction of the current. My fingers are pointing into the page, and my palm is pushing upward. So the direction that this wire is going to experience a force by the right-hand rule is in the upward direction. So this wire is going to get lifted in this direction, is the direction of the Lorentz force. So fingers in the direction of the X's, thumb in the direction of I, palm in the direction of F. I encourage you to pause the video, try that yourself, make sure you're comfortable with that illustration. This is something you will have to do on the IB exam and our unit test as well. So if we wanted to summarize what we just talked about, again, I'm not going to say anything about the Fleming left-hand rule. That's for you if you'd like to use that technique, if you come across it. I'm going to use this pushing right-hand rule. I think it's easier to remember. So you point your thumb in the direction of I, just like for the grip rule, your thumb is the direction of the current of your right hand. Your fingers in the direction of the magnetic field. It's like the field lines. And then your palm pushes in the direction of the force. Flip over to the next page. We're talking about the Lorentz force as the force on a current of wire, a long wire of length L or a wire of length L. What happens if it's not a current? What if it's just a single charge? What if I fling like an electron into a magnetic field? It will get a force. It's kind of like a little current. And what you have to be careful about is here, current is defined by convention to be positive charge, but if you have a single charge, it could be a negative one. Maybe it's just an electron. And if that's the case, then you have to reverse the direction, because an electron traveling this direction is the same thing as a current traveling the other direction. So you could treat this as if it's a positive charge traveling to the left. Or here's my personal preference. You can, whenever you have a negative charge, you could use the same pushing rule, except now switch hands. It'll reverse the direction. You can do it as a left-hand rule for negative charges and a right-hand rule for positive charges. I think it's easier to do it that way. So let's apply the left-hand rule, because this is a negatively charged electron. It's going from a region of no magnetic field to a magnetic field that points into the diagram. So I'll kind of zoom out here again so you can see my hand. So I'm using my left hand now. Okay. My thumb is pointing in the direction of, since it's the motion, which is to the right. My fingers are pointing into the diagram, into the page, and now my palm of my left hand is pushing down. So this electron, as it enters the magnetic field, right here it doesn't get a force, but as it comes into the magnetic field, we'll draw it right here. Okay. That's here, it's headed in this direction. It's going to experience a deflecting downward force, a Lorentz force that's going to push it downward. So instead of taking a straight path through this magnetic field, it's going to begin to curve. And just like in the case of our long extended current, we can see that the force is perpendicular to the motion. So there's a very important takeaway here. You think about how magnetic fields affect charges versus how electric field affects charges. A magnetic field, or a B field, can only turn or change the direction of a charge. It's always going to act perpendicular to the motion. So it's never going to push it forward to make it go faster or push against it to make it go slower. It will not do work. It will not speed up or slow down the charge. It will simply shift its direction. And it turns out that if you want to make a charge go faster or slower, you need an electric field for that. An electric field can push a charge and keep pushing it in the direction it's going to speed it up or slow it down. So let's think about what happens to this charge. It gets pulled downward. It's heading to the right. It gets pulled downward. What that's going to do is it's going to start to curve its path. And sometime later, the electron's going to be here, and it's not going to be headed to the right anymore. Now it's going to be headed in this direction. So if I apply the left-hand rule again, let's do that. We'll take my left fingers, point them into the drawing. Now my thumb, instead of pointing directly to the right, it's pointed kind of down at a slant. Now I can see my palm is pushing in this direction. Zoom in on this a little bit here. Now the force looks something like this. So the direction of force is changing. It's still perpendicular to the motion. And so it's going to continue to curve this charge. So the charge is going to move in an arc, a circular path, until it leaves the magnetic field. And if it's a big enough magnetic field, I could just trap this thing into a circle where it just continues to circle. And in a sense, it kind of orbits around the magnetic field lines as it goes around. The force on a single charge in a magnetic field, instead of a long flowing current, is equal to QVB sine theta. QVB sine theta. And where this function comes from, it's really the same equation, because remember we had the Lorentz force was equal to BIL sine theta. And I is just a flow of charge. So what we can do is we could take I and we could replace it with Q over T L sine theta. So here's our Q and here's our B, and then the L over T is just distance over time. So we replace the L over T with the V. So if we have a single charge, we can write it like this. And it's on the IB data sheet as well. And we use the same right-hand rule, or if it's a negative charge, left-hand rule, as we would for a long straight current. So if you have a charge in a magnetic field, one place where you might see this kind of crossover into some of our older topic material is you might see some circular motion begin to develop. And if you think about a charge that cuts into a magnetic field, maybe it has a force that's equal to QVB. If you think all the way back to topic 2, if that force becomes a centripetal force pulling in toward the center of a circle, that's going to be equal to mv squared over r. It's our equation for centripetal force. So in this expression, we can see that the v, one of the v's cancels out from both sides. And again, this one's not on the IB data sheet, but you might have to derive it or come up with the relationship by connecting magnetic force as a centripetal force. We can get an expression like this. This tells me the size of the circle that the charged particle will move in. What's interesting about this is we see there's actually the momentum of the particles in the numerator. So really massive particles or fast-moving particles are going to travel in big radius of curvature. Pretty much they're going to go straight. They're not going to turn in tight circles. But the stronger the magnetic field is, or the amount of charge you have, the tighter the circle will be. So if you send a charged particle into a cloud chamber and you can see the path that it makes and measure its radius, if you know any 3 of these variables, you can solve for the 4th one. You can predict. Maybe you know how strong your magnetic field is. Maybe you've measured how fast the particle's going. So maybe you're interested in knowing what its mass is or how much charge it has. You could solve for one of those. Another thing to keep in mind with the circulating charged particles is that they're going to orbit around the magnetic field lines, but they can travel along them as well. So the shape of a charged particle that's just kind of randomly thrown into a magnetic field tends to be a helix. You can kind of see that here with this charged particle. So you can see this charged particle has a velocity represented by this green vector v, and there's a component that's perpendicular to the field, and there's a component that's parallel to the field. Now it only gets a force from the perpendicular part of its motion, so it's going to circle around these field lines due to its perpendicular velocity, but it's going to continue to drift along them due to its horizontal component, parallel component. So field lines, magnetic field lines are good for trapping charged particles. Sometimes they call that a magnetic bottle, where the particles get trapped and they orbit along the field lines. You think about how the Earth's magnetic field behaves. This is actually one of the reasons why the Earth's magnetic field is essential to life on Earth. Is the sun is continuously, or not continuously, but periodically releasing big bursts of charged particles, generally protons, high energy protons toward the Earth. And if these protons slammed into Earth, we're talking about destruction to life and biological matter. But the Earth's magnetic field traps a lot of those. The particles hit the Earth's magnetic field lines and begin to orbit and loop around them. And what they'll tend to do is they'll tend to oscillate back and forth. The Earth acts as a magnetic bottle. And if ever enough of them come through at once, they'll actually kind of punch through and they'll get out and they'll hit the Earth's atmosphere. And they'll always do that near the northern or southern hemisphere. And you get the aurora borealis in the north and the aurora australis, the northern and the southern lights, happening as those charged particles hit the atmosphere. On to page 36. So currents experience forces from external magnetic fields. And then we know from the previous topic, the currents create their own magnetic fields. So currents push or pull on each other. And we can really use both right-hand rules to help us figure out how this is going to behave. These are some examples of some kinds of questions that might show up on IB exams. We've got two solenoids here, and there's like maybe an iron core, and a lot of times we'll put an iron core inside a solenoid so that its atomic magnetic domains line up and it enhances the effect. So back to previous activity, we're thinking, okay, here's the current. We can see the loops of wire going around this thing, and if we use our grip rule, we imagine like this wire that goes down in the front. If we imagine gripping that with my thumb pointing down, I can see that this is going to create magnetic field lines inside that are going to be pointing this way. So in this solenoid, the magnetic field lines are going to look something like this. They're going to point out of the right end into the left end. So in other words, the right end of this solenoid is going to act like the north pole where the field lines point away. And the left end is going to act like the south pole of a bar magnet. And I can do the same thing for this one. This time I use my grip rule, pointing my thumb upward for the current flowing upward in this part. And now my fingers point to the left. So this is going to create magnetic field lines that point in this direction. And so this end is going to act like a north pole, and this end is going to act like a south pole. And so I can see that the two north poles are butting against each other. These field lines are headed toward each other. And so these particular magnets, will repel each other. Since like poles repel, the two norths are going to repel each other. They'll push away. If I have, say, two long straight wires that are both carrying currents, let's say there's a current, we'll call this one current A, and we'll say there's another current over here, current B. Each one of these wires acts as a magnet that creates a field that then affects the other one. So what I can do is I can think about this in pieces. I could think about wire A as causing the magnetic field. So I'll use my grip rule for wire A. I'll imagine grasping that wire with my thumb pointing upward, which means that the field lines are kind of pointing around it like this by my grip rule. So over here in the vicinity of wire B, a magnetic field is going to be made that points into the diagram. So I could use my X symbol. This is the field caused by current A. It points into the diagram over here, and then it actually causes a field out of the diagram over here as those loops go around and come back in the other side. So I don't care what it does over here, though. It's going to make a field that points into the diagram here. So now I can use my pushing rule for current IB, and I can point my thumb in the upward direction and my fingers into the diagram in the direction of BA, and I can see that that current's going to get pushed to the left. So there's going to be a force this direction on that wire. Okay? So the wire is going to get pulled toward the other wire. And what could I do? What's going to happen to this wire? I could do the reverse. I could figure out, let me figure out what kind of current, what kind of field this one makes. So now I can imagine grasping wire IB with my thumb pointing upward. It's going to be making a field. So I'm going to call this one the field from B, BB. Okay, it's going to be pointing out over here. By the grip rule, it's making loops that go around like this. And then if I point, I'm going to kind of twist my hand around like this. A little hard to do with the dot cam here. There we go. So I'll point my thumb upward and my fingers coming out of the diagram, and this wire is going to get pushed to the right. So this one's going to experience a force in this direction. And I shouldn't be too surprised about that, because if you think about Newton's third law, if wire A pulls wire B to the left, then wire B has to pull wire A back to the right. And they're both going to get the same amount of force. It's a pair of forces via Newton's third law. And the takeaway really is that whenever two currents are doing the same thing, you kind of think about them like people. They're two people headed the same direction in life. They attract each other. They like each other. It's when the currents point in opposite directions or do opposite things that they're going to repel one another. So we could say currents attract if they're in the same direction and repel if they are opposite. So you can see that with a straight wire. You should also be able to see that for like a loop or a coil of wire. If these are two loops of current, so let's say this is a current I and this is a current I. By the grip rule, they're creating magnetic field lines that point upward, which means the top of the loop is going to be like the North Pole and the bottom is going to be a South Pole. They're both doing the same thing. So north here and south there, these two loops are going to attract each other, just like the two wires attracted each other, the two long straight wires. So as we wrap things up here, we think about how currents are affected by magnetic fields. This takes us to the way that current was originally defined as a metric unit. The original definition of the ampere is defined to be when F equals 2 times 10 to the negative 7th newtons. Actually 2 times 10 to the negative 7th newtons per meter on two wires that are a meter apart. So how do you know that you have an ampere of current? When you have this amount of force attracting two wires that are a meter apart. That was originally the definition of the ampere. However, that definition has changed. It's difficult to make that measurement exactly. And so as recently as 2019, instead of defining the ampere and then using that to define charge, it was decided by the powers that be that they were going to fix the value of the elementary charge. And so the elementary charge E is given an exact value, and then the ampere is defined in terms of that. So the elementary charge, the charge of an electron or a proton, is 1.602176634 exactly times 10 to the negative 19th coulombs. It's not a rounded number, it's the exact number. And then now the ampere is defined to be 1 coulomb per second flowing by. So it used to be the other way around. Now it's based on the elementary charge. So that's the end of the new material, really the end of the topic. Let's look at a couple example problems and we'll be finished. Quickly noting what's on the IB data sheet, two new formulas. We have the formula for the force on a single charge particle and the force on a current. You're expected to know the right-hand rule, or in the case of a negative particle, the left-hand rule for pushing, as well as the gripping rule for figuring out which way the fields are from currents. One, one helpful hint to think about is many of you guys are right-handed. So when you're taking an exam, it's very tempting to be writing with your pencil with your right hand and then to use your left hand to try to do the rules. You have to remind yourself deliberately to put your pencil down or your pen down and use your right hand for the right hand rule. It's a very common mistake to use the wrong hand for the rule. Of course, you'll get the opposite answer. All right, let's take a look at these three. So the first question gives me three parallel currents, PQ and R, PR and Q. Each wire has the same magnitude of current in the direction shown. Describe the direction of the force acting on wire Q, that's the middle wire, due to P and R. So this one's pretty quick. If you know the pattern, you should be able to get these quickly. Looking at how it interacts with P, they both are carrying current downward, so they're going to attract each other. It's going to get pulled toward, so we'll call this the force from wire P, FP. On the other hand, wire Q is carrying current in the opposite direction of wire R, so they're going to repel each other. So the force from wire R is going to be this direction. Okay. Now, these wires are going to push on each other too, but the question was only about what happens to this one. It gets two forces to the left. So we're asked the direction of the force on it. So it's rather than a canceling effect, it's a force to the left. The middle wire is definitely going to get pushed to the left by the other two wires. The second problem, we have an electron entering. This is very much like a kind of a bigger picture IB type question. It's entering two fields at the same time. It's entering an electric field that points downward and a magnetic field that points into the page. So it's going to get two forces. But to think about those two forces, I have to recall that the force on a charge in an electric field is equal to the charge times the field that it's in. And the force on a charge from a magnetic field, we just learned that today, is QVB sine theta. So it's getting two forces potentially. Okay. Now I'm given the strength of the electric field and the strength of the magnetic field, and I have to calculate the speed of the electron if the net force acting on due to the fields is 0. So I have to think about the directions of these forces. The electron comes into the field. Here's my electron. The electron is heading to the right. Okay. There's an electric field that points downward. Now the electric field shows which way positive charges get a force. So the electron's going to get a force the opposite way. The electric force on this electron is to get pulled in the upward direction. And that's true whether it's moving or sitting still. It's in a downward electric field, it's going to get an upward force. But because it's moving, because it has a velocity to the right, okay, because it's an electron, I have to use my left-hand rule, and I point my thumb in the direction of the motion and my fingers into the drawing in the direction of the magnetic field. The magnetic force is going to point in this direction, which is implied by the problem. It says the forces cancel out. So these two forces are the same size. They're going to cancel out, and this electron's just going to travel in a straight line. Okay. These forces are equal in magnitude. Now, to simplify things here, the angle theta is the angle between the motion and the field. So the charge is moving to the right. The field points into the diagram. Those are perpendicular to each other. Sine of 90 is just 1. These two are equal to each other, so I can set QE equal to QVB. The fields are balanced. The fact that it's an electron doesn't even matter. Any charged particle entering the field at this speed is going to have a balance because the amount of charge and even its sign cancels out. And I find the speed of my particle has to be, for this balance to occur, right? The magnetic effect is speed dependent. There's only one speed where this will happen, is equal to the ratio of the two fields, E over B. So if we plug the numbers in, we'll just make sure they're in base units. So yeah, volts per meter, base units 3.8 times 10 to the 5 volts per meter. And then Tesla is the base unit for magnetic flux density, 2.5 times 10 to the negative 2 Tesla. We can get the speed of our electron, and it ends up being in meters per second. It's kind of fun. 1.5 times 10 to the 7th meters per second, which is getting close to the speed of light, which is hard to do for a big thing, but fairly easy to do for an electron. Let's finish. We're almost there. Final problem. Number 3, here we have a current. We can see the wire in the magnetic field. So here's my magnetic field B. Here's my current I. They make an angle to each other. We're told the angle is 30 degrees. We have to find the size of the force on this wire, magnitude, and direction. So since this is a long straight wire, this is Bill sine theta off the IB data sheet. And I'm given these values. I'm told the magnetic field, 0.058 Tesla. Current is 35 amperes. That's a lot of current. The length of the wire is 0.75 meters. And this isn't quite perpendicular. It's not parallel either. Oops, I almost tried to do a cosine there. Sine of theta is 30 degrees. Sine of 30 degrees. We get the magnitude of the force. This wire is going to experience about 3/4 of a Newton, 0.76 newtons of force. So the final step is for me to figure out which way this wire is going to get that force. So I have to use my right-hand rule here. The magnetic field points to the right. Current's flowing down at an angle like this. So I have to take my right hand. I have to point my thumb in the direction of I and my fingers in the direction of B. I'm going to kind of get myself up here so I can rotate myself around here. So my fingers in the direction of B, my thumb in the direction of I, and my hand is pushing up out of the page. My palm is pushing out of the page. So the direction of force out of the page would look something like this. This wire is going to get pulled towards us, say out of the page. There you go. There's the last lecture for topic 5 and example problems. Go to town on the activity. Have some fun.